In the previous video, we did a bit of an introduction to the Aquarius rating curve development environment, and we passed in a little bit of data for specific drainage. Now that's the data I'm going to use for developing a rating curve in this particular case. Now the first thing I want to do when developing a new rating curve is select the measurements which would be appropriate for this particular curve. So what I'm going to do is go to the time series view, and I'm zoomed in right now. I could zoom all the way back out and have a look at my measurements dating back in time. I have quite a few old measurements. These are fairly typical, the high water measurements from back in previous years. We can look here, I've got some discharge at 250 CFS, or in fact this is cubic meters per second I'm dealing with right now. So we could zoom in and look at the most recent measurements down at the low flow end. And we may not want to use all of these measurements. If I look up in my site visit data pane, now I'm just going to pin this off to the side so we get a little bit more room to play with. We're going to see that some of these measurements are taken under aggregated conditions. Now if I click on the measurement here, it's going to show up as a haloed measurement right here. And this is one I probably want to switch off because I don't want to build my base rating curve for when I have an aggregated control. So I'm going to switch off those two measurements. And you can actually sort by control condition. I have another one right here. I probably want to turn that one off. Now I'm going to use the clear measurements and my high flow measurements, and I'm going to turn off the scour measurements, and I have one here with unspecified conditions at the site. So that may be one that I want to be aware of when I'm developing my rating curve. So those are a few measurements I've switched off. And you've noticed when I check the status box off here, they gray out in all of the other panes. So a few measurements here have grayed out, as well as the various other zoom panes. I've just switched a whole lot of measurements off here. So the gray ones are now switched off. So what we're going to do now is develop a rating curve. Now to develop a rating curve, we need to understand the control conditions at a particular site. In this particular example, I know when my gauge height comes up around 37.5 meters, I'm in a transition zone. I'm changing from section control to a channel control. So in terms of dealing with the physics of this particular site, I want to develop one curve or one section of curve that's going to define the physics at the bottom end, and I want to define another section of curve that's going to define the physics at the high end of my curve. And I'm going to want a transition zone in between the two. And this point right here, this purple one right here, if I turn this one on, let's have a look, measurement 57 at around 37.5. This is really my transition zone of about 2.5 QMEX coming through. When I'm below that, I'm definitely in section control. When I'm above that, I'm definitely out into a different control feature, usually channel control I think I'm in right now. So to develop a curve for the low end, I probably don't need my high end measurements switched on. So I'm actually going to use the turn off measurement tool, and I'm going to switch off my high end measurements. You can actually make those measurements turn invisible if you want to. In the top controls here, there's a button here for show hide unselected measurements. And I can actually make them go completely invisible. I'll actually keep mine on just for the sake of knowing that they're there. But if you want to during your development, you can actually turn them off completely. So we're going to keep them on. The next thing we need to do is start defining the offset. Now, if I just pull out a little bit of I'll just pull out a notepad here. So I'll talk a little bit about the hydraulics equations that we're going to be dealing with. So essentially, the most basic thing we can talk about in terms of hydraulics is that discharge is related to flow, usually by some parameter A, time, which is geometric, times our hydraulic head raised to some power. Now that power is going to depend on the flow conditions we're in. Usually it's 1.67. It'll be in the range of about 1.3 to about 2.8, maybe up to 3, depending on your flow conditions. Generally speaking, for a section control, you're dealing with a value that's around 1.67, depending on the particular conditions at the site. Now the problem we have is we don't measure head. We measure gauge height. Now gauge height is related to head, but it's related through an offset E. So if we look at this, we have our head equal to the gauge height minus some offset E. Now if we do a simple substitution, we get an equation of the form Q equals A times, and if we look at this value now, it's going to, instead of going to be H, it's going to be gauge height minus the offset E, and we'll put the exponent outside, raised to the power of 1.67. So that's your most basic simplification of Manning's equation and flow equations. This is essentially what we're doing. Now the nice thing about developing things in log-log space is if we take a log transform of this equation, we're going to get the log of Q, make that capitalized, is going to equal the log of the entire right-hand side. Now the first law of logarithms, well, I'll just do the whole log of the whole right-hand side in here, just so we do this step by step so everyone can follow. Now the first law of logarithms allows us to turn that multiplication into an addition if we spread the log across both sides. So I'm going to copy this line down and make another line, and what we're going to do is change this equation now, and we're going to go, instead of multiplication, we're going to do addition, and I'm going to do another log operator right there. So now we've got an equation in two parts. Now the second law of logarithms allows me to take this exponent and roll it down in front. I always got a real kick out of the fact that you could roll exponents with logs, sort of like rolling a log. At any rate, let's just copy that equation back down. And we'll put it right there. Now we're going to take the exponent from here, and I'm going to cut that out of there, and we'll just tidy up the brackets a little bit. And that allows me to put the 1.67 multiplied by out front. And I'll clean up the bracket in there as well. So the nice thing about that equation is it's actually a linear form. So your standard y equals mx plus b that we all learned in school, this is a linear equation once we do a log transform. And that's really why we develop curves in log-log space. So the key is going to be getting this offset value here to make our measurements that are hydraulic points fall into a nice straight line. So we can do that using the offset manager. We look at our measurements down here, and actually for the sake of this, I'm actually going to switch off my other measurements, just so we're just looking at these points, and I'm going to switch on my offset. Now my offset in this case is usually, or in my offset in most cases, is the point of zero flow, especially when we're dealing with section control. So if you know the bottom of your control feature, you know what gauge height that is, that's generally a good starting point for what your first offset should be. In addition to that, I'm going to choose to plot to that offset. So I'm going to adjust the scale of my log-log space to offset 1. Now as I change these points, you can see my scales over on the left-hand side. In all of my graphs, they start to change. Now I can tick them up one at a time here, but that's actually a long way to go. I know I've got to go all the way to 36.7-ish. So I'm going to start by just going into and typing 36. Maybe we'll go to 36.4. And you can see the geometry of my points has now changed. They're still plotting in the correct position. If you click on any one of these, you can see this is 37.5. Well, it's plotting in the right place for 37.5. And a discharge of 2.33. Well, that's 2.33 in log-log space as well. So still plotting in the correct position. But what I'm doing is adjusting the scale factor here. And you can see, as I keep on adjusting that, those measurements start to fall in a straight line. Now, if you go too far, the measurements start to fall into negative log-log space, which tends not to exist. So you can see there, I get a pretty straight line around there. Now, how do you know if you've got a straight line? Well, you could put a ruler up to the screen, or a more easy way to do it would be to start adding rating points. And the lines drawn in between rating points are straight lines in log-log space. So they actually represent those hydraulic equations that we were dealing with earlier. So what I'm going to do is grab the Add Rating Point tool, add a rating point somewhere down at the bottom. You can move it afterwards, so I'll just click to add it. And I'll click another one somewhere up at the top, and you get a straight line in between. You can click to move these points around if you want, so you can always click and drag them, move those points around. And you'll see here, if I change my offset, I always get a straight line in between those rating points, but my measurements no longer fall in a straight line. So you can see here, you really start to get that straight line, your measurements falling in that straight line. And you can get a little bit neurotic here, and you can start adjusting by 0.1s if you want to. You can change your adjustment step down at the bottom. Instead of being every 10 centimeters, I could go 0.1 centimeters, and then as I adjust here, I'd be adding very small values. But you have to remember what you're actually adjusting here. I mean, how well do you actually know the point of zero flow of your control? You probably don't want to go into minutia here. You can definitely look at the statistics and see whether you're significantly above or below. You want to look at that sum of the errors, see whether you're systematically above and below. And I'd say a value of 36.71 is probably pretty good for this, especially I don't want to really get into quibbling about a centimeter here and there at the bottom end of the control. So that's fairly good in terms of linearization of those measurements. If we actually want to look at what the equation is defined in between there and do a bit of a gut check, and is this a hydraulic relationship, let's have a look at the rating table. So I'll bring that out from the side. If I just expand that out, you can see here I've got an equation that's relating my discharge to my flow. In this case, it's just denoted as x and y. And the y value, because that's your actual gauge heights here. We always deal with things a little rotated by 90 degrees in hydrology because water levels go up and down. And you can see the actual equation. You can see the offset, minus 36.71. That's what we define in the offset manager. The geometric factor is being defined for you by where you put those actual points down. And you have this slope factor, or the slope once you've done the log transform, or the power. And in this case, 1.887. So definitely in the physical range of about 1.3 to about 3, depending on the control conditions you're in. So certainly all the gut checks are working here. We could go and have a look at this in rectilinear space. We could zoom right in. You can see the scales are a little bit off here. Let's zoom all the way down in. And you can start to see that really nice hydraulic relationship down at the bottom end of the control. So by defining a straight line in log-log space, we've defined that straight curve in rectilinear space. And you can, of course, adjust things a little bit in log-log space. You can move these points around. You can move them in rectilinear space. And I've got my automatic rating scale on, so when I drop that, it's going to zoom me back out. Just going to do the same in here. So there are definitely two ways to skin the cat in here. And you can work in log-log space, or you can work in rectilinear space if you want to. So we've defined the bottom end of this curve. in terms of the section control points. One other thing we should definitely be doing at this point is defining a period of applicability for this particular rating curve. Right now we still don't have a period of applicability, so I definitely want to go into my rating period manager and say when is this curve going to be effective for. And to do that, I definitely want to look at the time series manager. So I've got measurements here that span, the ones that are switched on span about January 2007 to around January 2008. I could say my curve is going to be applicable for those dates, so I'll double click on this one, the rating period here. I will assign it a rating period, and I'll say let's go from 1/1/2007 to an end date of 1/1/2008. 2008, if I click it correctly. I could put remarks in here if I wanted to. Right now my station or my rating curve is assigned the number 001, and it's a stage discharge curve. This is the computation code here is again a bit of USGS terminology, so folks in the USGS will be familiar with this. Other folks don't really need to worry about it. There we go. I now have a date of applicability. You can see down here in the time series view that rating period has been assigned, big red bar. If I wanted to adjust that, I can certainly do that in the time series view. I can use the time slider or the date adjuster right there. And if I click on that bar, I can actually adjust the end dates forward and backwards. So if I wanted to do it just for the time series data where I have data available, I could trim those bars in a little bit. And this is going to be very useful when we develop shifts. We're going to talk about that in the next video. Developing a shift, you may want to shift directly to the peak of a hydrograph. Because that may be when you start filling instead of scouring. So you can talk about the energy of your creeks coming up and down. We'll definitely talk a little bit about that. Other things we want to do here is develop a rating curve for the high end. So we've conveniently, or so far, I've conveniently ignored the measurements that fall at the very high end of my curve. And I'm going to switch those back on. We'll click those back on. And you can see 3 very high end measurements up here at the top. What I'm going to do is I'm going to switch those measurements on using the switch on or select measurement points tool. So I'm going to turn those ones on, and I'm actually going to switch off everything below the control. So those 4 measurements down there below, we'll switch those ones off. Another thing worth noting is now that I've defined the periods of applicability of my rating curve, any measurements I switch on that are within that period of applicability show up as larger dots, and they'll be annotated with their measurement number. So you can see that for measurement 57 right there. Now moving on, let's talk about developing of the rating curve at the high end of flow. You can see those measurements, even though we're plotting right now to the first offset, they're still not falling in a straight line. And that's generally the case when we deal with channel flows that fall above section controls. Now we may have a low point in the section control that is not actually the effective point of zero flow for a channel flow. So we may actually be dealing with a second offset, or essentially there's a second section of physics that defines the flow at higher flows. In order to make that transition, what we need to do is define a second offset. By defining a second offset, we also need to define a breakpoint in between where those offsets apply to each other. So in the offset manager, you can define a second offset just by clicking up here. Now, offset breakpoints need to be rating points in between that are defined on your curve. Now I've just got 2 points here, so I'm using the top one, and points above this are going to be defined using my second offset, or the curve above there is going to be defined using my second offset. So what I'm going to do is I can start playing around with that top offset, and I can choose to plot to that top offset. And in this case, I know it's probably going to be slightly larger because an effective point of zero flow will generally be larger than your actual point of zero flow in terms of gauge height. So maybe I'll go to a value here of maybe 36.8 as a starting point. We can see how those measurements start to fall into a straight line. Slightly more than they were before, and you can see how the bottom end of the curve starts to distort a little bit here. If you continue to want to see the bottom end of your curve plotted as a straight line, you can choose the option of plotting to multiple offsets. And what that'll do is your top end measurements will be plotted relative to their offset, and the bottom end measurements will be plotted relative to their adjustment. The difficulty with this is when you start drawing a rating curve with this particular plotting option, you can actually get a discontinuous curve, and I can show that just by adding a rating point right there. If I increase this offset significantly, you can see I actually get a discontinuous curve. So generally speaking, when I'm developing these curves, I like to see them as continuous curves. So I'll just ignore the bottom end of the curve while I'm plotting to the second offset, because the plot really doesn't apply down at the bottom end. So I'm going to do exactly like I did before for the bottom end of the curve. I'm going to adjust that offset to try and make that straight line that I've added at the top end hit those measurements. We can see how we're gradually closing in on those measurements. Still got 44% error associated with that. I'm going to increase my steps so I can move a little faster. We'll adjust by 10 centimeters at a time, and we'll keep moving upwards. There we go, around 37.2. I'll just set that to a round number. Let's have a look whether we're systematically over or systematically under. Looks like we've got a percent error here of 6%. That's probably very good considering the way that measurement was probably taken. There's a fairly large error associated with that, about 10% error on that one. The high end measurement, let's see how we're doing, 4% error there. So definitely doing quite well. If we scale the shift diagram, we can actually look at our residuals relative to it. So these are our measurements falling relative to the curve. That's what the shift diagram shows you actually. The zero line here always represents the curve. We'll get more into what the shift diagram represents, but it's actually a fairly useful tool for looking at residuals. And you can see as I adjust my offsets, my measurements move relative to my line. So I'm looking for systematic bias upwards or downwards, and you definitely want to fall within the error bars. So maybe somewhere in there, about 5 centimeters up, would be a pretty good value. Now I'm definitely hitting those values fairly well. If you look at the curve in rectilinear space now, let's just zoom ourselves out a little bit. There we go. You can see the high end of the curve relative to the low end of the curve. So generally speaking, we've got a pretty good fit up there. I may want to adjust that high end point a little bit to really get in on that high end stage value. And when I let go of that point, you're going to see my shift diagrams all update on the fly. So if I go a little bit past it, I'll get that top error bar once more. There we go. That point shows up. So definitely a good high end to the curve. If we look at our rating table, once again, we're going to see that given that new offset, we continue on with much the same slope as we had, or power that we had before. You can see the geometry factor has changed here significantly, and our offset factor has changed again. So I've defined that second sort of order of physics that's going to take us to the next level in terms of this rating curve. Now, the next thing we may want to do is extrapolation of the rating curve. Now, typically you won't be able to go out into the field and measure your highest end flows. These are going to be flows during flood conditions when it's either not safe or you just happen not to catch the peak of this particular hydrograph. So in order to actually calculate discharges associated with those very high gauge heights, we need to do a certain order of extrapolation. And for this, we have a tool. It's called the Extend Rating in a Straight Line. And you can see here my top end line. If I click this tool, it's going to add another rating point in the straight line continuing on above it. And if I click and drag it, it'll only let me move it in a straight line above where that original point is. And I can drop it right in there. Now, rules of thumb associated with extrapolation of rating curves. You generally don't want to go above twice the measured discharge, and you never want to go above a stage value or extend above a stage value where you have a significant change in geometry of your channel or a change in the flow conditions. So if you're extrapolating channel flow, you definitely don't want to extrapolate it out onto the floodplain, and likewise for a section control. You definitely can't extrapolate a section control order of physics up into channel where a section control might drown out into a channel control. So in this case, I've probably gone a little bit too far. Let's look at my rating table. My highest measured discharge, actually if I look at my site visit data, let's look at my measured discharges, was up at 250 QMEX. So my highest rating point is 255, slightly above that. I definitely wouldn't want to go above 500 in this particular case, and I wouldn't want to go above a stage value that corresponded to a break in the channel. So I'm going to want to bring this one back down, probably to around 500. Let's just go back into my rating table and have a check. There, quite close to 500 right there. And I want to make absolutely sure that the stage value I've extrapolated up to doesn't break onto any new features in terms of the floodplain or the channel. So in this case, I know I'm fairly safe. I don't break onto the channel here until around 41 meters. So that's probably a fairly safe extrapolation of the curve. So that's really what we're doing in terms of rating development. We've extended the top end of the curve. We've developed the bottom end using log-log space. We've talked about using multiple offsets to control various physics. We can plot to multiple offsets. We can plot to a single offset if we want to see the entire curve relative to its own offsets. We're going to see it in a discontinuous space though. If you're plotting to single offsets, you're going to see the top end in a curved space. It's not linear because you're not adjusting the scale to the correct offset. And again, if you plot to second offset, the bottom end of the curve is going to drop off the end of the log-log space. And that's really the visualization of development of a rating curve. Other tools we can use are looking at error statistics. So this is the sum of the statistics, sum of the minimum errors, maximum errors, root mean square, and the sum of all the errors on the measurements that are switched on. We can also use the site visit data table. And on the last columns of this, we have a few additional columns that will tell us the percent errors associated with the various measurements relative to the rating curve, and it'll only compute these for the measurements which are switched on. So if you're interested in a specific measurement, you can switch it on, go and have a look. And this one, that happens to be, let's see, an aggregate condition, and it's 40% away from the rating curve. So that's really one we're going to want to deal with in a shift, which is the topic of the next video. So that's it. Now you know how to develop rating curves in the Aquarius rating curve development environment.